Okay, we are building to being able to look at a vector field and perform a test on it to see whether it is conservative or not. And then if it is conservative, we'll actually be able to find a potential function, okay? So that we can take advantage of some of these nifty properties about conservative vector fields being independent of path, and the work around any closed path being zero if it's a conservative vector field, okay? Before we're ready to do that, I need to just define some vocabulary, okay? And it's going to feel like this is just sort of a timeout, has nothing to do with things, but this vocabulary is going to be necessary in stating the theorems to establish the test for how we know whether something is conservative or not. Okay. So with curves, okay, I've already defined what a closed curve is. That just means the starting point is equal to the ending point. Okay. So I could have just a simple loop like so. I could have something more convoluted like so, and I'm just highlighting a point to say that's my starting and ending point. And I could have something that intersects itself like so. I could even have that point of intersection be the starting and ending point. That would be totally fine as well. So that's what a closed curve is. Okay. A simple curve is one that does not intersect itself, except possibly at the starting and ending point. If I didn't have that exception in there, it wouldn't be possible to have a curve that was both simple and closed. Okay? But we'll see in a moment, that's both. That's simple and closed. Okay. So, a simple closed curve is going to be a curve that only intersects itself at the starting point, which is the same as the ending point. Okay, all of those words don't, well, they explain things, but I don't think they illustrate it nearly as well as an illustration would. Okay, so I'm just going to give you some examples of curves that do and do not have these properties. Okay. So, this would be an example of a curve that is not simple because it intersects itself at that point, and it's not closed because it doesn't return to its starting point. Okay. This would be an example of a curve that is simple. It doesn't intersect itself, but it's not closed. Okay. This would be an example of a curve that is not simple, but is closed. Now you might say, what if I made that the starting and ending point? Could I then view this as closed? And the answer is no, because if I start here and I come around like so, I'm intersecting that same point, but I'm not yet at my ending point because I still have to do this second loop. So I'm hitting that point more than just at the starting and ending point, so this would not be a simple curve, but it is closed. And this would be an example of a curve that is both simple and closed. Okay. So notice it's two concepts, and you can have one or the other, or both, or neither. So any of these possible combinations. Okay. This makes a great short answer question on a test. I can just ask you, rather than to recite the definition, draw me an example. Okay, so that's our vocabulary that has to do with curves. The next bit of vocabulary has to do with regions. So this will be regions in 2 space or 3 space. And So generally we're thinking of things that would have area or volume to them, depending on whether we're in 2 or 3 space. Now I already mentioned what it meant for a region to be connected. Informally, that just means it comes in one piece. We don't have separate pieces. The more formal definition is if I have 2 points in the region, I can draw a curve through the region that goes from the first point to the second point. Okay. Simply connected is what we need. Simply connected, very informally, means no holes. Okay, so no holes in the region. Okay, so a disk is simply connected. There are no holes. A donut is not simply connected because it has a hole. And of course, the notion simply connected only applies to connected regions. If it's not connected, there's no way we can modify the word connected to make it simply connected. So a connected region is simply connected if very informally it has no holes. Now, in 2 space, we can define that more formally. So in 2 space, a region is simply connected if no simple closed curve in, let's call the region D, no simple closed curve in D encloses points not in D. So that essentially is defining what it means to have a hole in it. Here's a simple closed curve that's contained in that region D, but notice inside of that curve there are some points that are not in the region D, so that defines what it means to have a hole in it. Okay. Now, for 3 space, I can still think of simply connected as meaning sort of informally no holes, but it's a little bit trickier to work with that. If I have something like a paraboloid, and I look at this curve right here, so just a finite section of a paraboloid, and I look at this curve here, that's a circle, it looks like it's enclosing points that are not inside that paraboloid, assuming I'm just talking about the surface of that paraboloid. Okay. So here, I've got a bowl, okay, so we're talking about like this circle right here. Now certainly, where I'm putting my finger looks like it's inside of that circle, but it's not part of the bowl. However, that's not a hole because I can't go all the way through. Okay, so in 3 space, it's possible to look like there's a hole, but it's not actually a hole. Okay, now we can define precisely what is meant by simply connected in 3 space, but it goes into a lot more geometry than we really need for this class. I think for this class we're good enough with an informal understanding of no holes. Okay, I will tell you that all of 3 space is simply connected. It doesn't come with any holes in it. Okay, and most regions that we work with, it should be fairly obvious if they are or are not, but I will just tell you if we're in 3 space, hey, this region is simply connected if it's not clear that it is. Obviously, like a solid sphere, something like that would definitely be simply connected. Okay, so those are our definitions. I will just point out one region that's a very common region in 2 space that is not simply connected would be all of 2 space minus the origin. So if I have R2 minus the set consisting of the origin, we can actually write it that way. Okay. What that looks like is there would be a hole here at the origin, but we'd have everything else. Now, obviously, that region has a hole in it, so it is not simply connected. Okay. The reason this one is important is because this is the domain for an awful lot of functions and vector fields that we have, anything that has the magnitude of r, where r was our position vector, so xy, okay, so if r equals xy, the magnitude of r is the square root of x squared plus y squared. That, of course, is 0 at the origin, but there are lots of important functions that have this in the denominator of them. So we're going to encounter lots of places that do work with this not simply connected region. Now, simply connected regions also make great short answer questions. I can ask you to draw me a region that is connected but not simply connected, or that is simply connected. In the past, I have done that on exams, and I've asked for a region that was connected but not simply connected, and people have drawn me this. Technically, they are right. This would be a degenerate region. It's not shaded in. It's just the circle, not the disk. If you meant it to be shaded in, you'd have to shade it in, okay? So technically, that curve is a degenerate region. It has 0 area, but it is a collection of points in 2 space, so it's a region of 2 space. And certainly, it's not simply, it is connected, but it's not simply connected, because the curve that it is encloses points that are not in it. Okay. Now, when people put that on an exam, even though they were technically right, I knew they hadn't been thinking that. I knew that they were just confusing simply connected and not simply connected regions with simple closed curves and things like that. Okay. So, just to let you know, if I ask for this on an exam, I'm likely to specify, give me a region with non-zero area that is connected but not simply connected. And then you would have to, in order to get the non-zero area, shade part of it and give me something like a donut. Okay? I just want to warn you about that, because when you first see that, you can be like, wait, what's this with non-zero area? What's the significance of that? That just says if I'm asking for a region, I don't want a curve. I don't want a degenerate region. I want a region that actually has some area to it if we're in 2 space, or some volume to it if we're in 3 space.